Okay, this is Core Pure 2 again, Edexcel, and it's last year's paper, June 2023. It's question 6. It's a proof by induction question, but a slightly unusual one in that you're proving induction with a differential. We've got the nth differential here of a function, e to 2x sine x, and we have to show that the nth differential of that function is this, where we've got our n's in here, 3 to the n here, so a little bit of work to do with this. Takes the same route that you would normally do with any particular induction. We're going to prove it for a simple case, n equals 1. So we consider n equals 1. So the left-hand side of this, the differential of this, dy by dx, so we're differentiating this. Product rule, two things multiplied together. Looks like we're going to go product rule on this, so we might call our u e to the 2x, and when we differentiate that, u dash is going to be 2e to the 2x, nice and simple. And then our v is sine x, and hopefully we know that when we differentiate that, we just get cos x. So when we differentiate, we do our product rule. We're going to be doing e to the 2x times cos x plus, squeeze it in under here, 2e to the 2x sine x. Oops, that's a bit messy, but hopefully you can see it going down at an angle there. Right, so that's what dy by dx is. Now we're going to show that when n equals 1 and we stick it in there, we get exactly the same. So consider n equals 1, dy by dx is that, and then n equals 1, dy by dx equals, let's put our 1 in there, so we get e to the 2x. 1 in there is going to give us 3 to the 1 plus 1 over 2, and really make sure they know that you're putting everything in. You're not taking any shortcuts here. Cos x. So that's e to the 2x, 3 to the 1 plus 1 over 2 is 2. 3 to the 1 minus 1 over 2 is 1, so that's just cos x. And let's go whole hog now. That times that is e to the 2x cos x, and then that times that is your 2e to the 2x sine x. So therefore, true for n equals 1. We've shown that it works for the very simplest case, the first case. We now go to the assumption. So we're going to assume it's true for a particular value of n. Usually we use n equals k there. So we've done the simple case. So we're going to assume true for n equals k. So that means the kth differential of this is going to fit this rule, e to the 2x, 3 to the k plus 1 over 2 sine x plus 3 to the k minus 1 over 2 cos x. Squeeze that in there. Okay, so we're going to assume that's true. We're now going to consider n equals k plus 1. So we're going to look at the k plus 1 differential of this. K plus 1 y dx, the k plus 1. Okay, so we're going to consider that differential, which means we're going to have to differentiate this again to go from the kth differential to the k plus 1 differential. We're just going to have to differentiate this function again. And again, it's going to be a product rule. Now you might times these out and do two separate product rules, but I think it's much easier if you just go, right, let my u be that and my v be that whole function there. So I'll rub that out and I'll do my u and a v over here. So nice easy, u equals e to the 2x, so therefore u dash is 2e to the 2x. Okay, so the differential of that. And now I'm going to do the differential of this. So v equals 3 to the k plus, 3 to the k plus 1 over 2 sine x plus 3 to the k minus 1 over 2 cos x. So if I differentiate that, I'll have to write it underneath to give myself a little bit of space. 3 to the k plus 1 over 2 is just a number. You know, k is something, whatever k is. It's not a variable in this particular situation. 3 to the k plus 1 over 2 is just a number. So it's like having 7 sine x there that we differentiate. And if we differentiate 7 sine x, we get 7 cos x. So differentiate this and you just get 3 to the k plus 1 over 2 cos x. And similarly, 3k minus 1 over 2, just a number. So when we differentiate this, we're going to just get 3k minus 1 over 2 sine x. Which means that when we get our k plus 1 differential, dx to the k plus 1, we're going to get e to the 2x times the differential of that, and 2e to the 2x times that. Right, this is going to be a bit messy, but it's going to struggle to fit this all on one line, but I'll do my best. So I might have to write a little bit small. E to the 2x times the differential of this, so we're going to have 3k, good start, 3 to the k plus 1 over 2 cos x. I'm going to do this in 2 lines, I'm afraid. So here, let me write it a bit better. 3 to the k plus 1 over 2 cos x plus 3 to the k minus 1 over 2 sine x plus, so we've done u times dv by dx plus v times du by dx. So that's going to be plus 2e to the 2x times that. 3 to the k plus 1 over 2 sine x plus 3 to the k minus that. Do that, keep doing that, over 2 cos x. Whew. Now the joy of just using that as your u and that as your v is you can see, it's going to be really nice and easy just to take out my e to the 2x. I'm going to bring this 2 into here and cancel those 2's. I'll just try and do it in one step if that's okay. So, give myself a bit of space. Where are we up to? Yeah, we've got that now. I'll just leave that there. So, our k plus 1th differential is going to look like, let's take that e to the 2x out of both of them, so e to the 2x. This, we're going to have 3 to the k plus 1 over 2 cos x plus 3 to the k minus 1 over 2 sine x, and then bring in these in as well, so 2 times that, the 2's will cancel, so I'm just going to have 3 to the k plus 1 sine x. Might put a bracket around that just to make sure we're nice and clear that it's all being times by sine x, and then 3 to the k minus 1 cos x. Whew. And then obviously I'm now going to put my sine x's together and my cos x's together. So that's going to equal e to the 2x. Now, which one do we first? Let's do the sine one first. So we've got 3k minus 1 over 2, lots of sine x, plus 3k minus 1, plus 3k plus 1, lots of sine x. So if you want, let's just put all of this, kind of factorise out the sine x if you like. So I've got 3 to the k minus 1 over 2 plus 3 to the k plus 1, lots of sine x, plus, now let's do the cos x's, so 3k to the k plus 1 over 2, 2, and then the other cosh x plus 3 to the k minus 1 cosh x. Whew. Okay, bit of simplifying now. So, think of these as two separate fractions. 3 to the k over 2, or if you like, a half of 3 to the k, minus 1 over 2. So, yeah, I'll show you what I mean by this. So if I separate that out into 3 to the k over 2 minus 1 over 2, plus 3 to the k plus 1, so that's that whole bracket I've written out with these just separate fractions. Isn't this just like half of 3 to the k? Plus 1 of 3 to the k, isn't that 1 and a half lots of 3 to the k, or 3 over 2 lots of 3 to the k? So, I've got 3 over 2 lots of 3 to the k, yeah? Minus a half plus 1, plus a half. Lots of shine x there. And then over here, I'm going to have the same situation. 3 to the k over 2 plus 3, so that's 3 over 2 again, 3 to the k. And then I'm going to have a half minus 1, so that's minus a half cosh x. Okay, so what can I do now? Well, 3 over 2 plus a half, so isn't that, I'm taking perhaps even more steps than I need here, but I'll do this. 3 times 3 to the k, I use the dot notation for this, plus 1, all over 2, lots of shine x. And then over here I'm going to do exactly the same. I've got 3 times 3 to the k, minus 1 over 2 cosh x. And 3 times 3 to the k is 3 to the k plus 1. So we got 3 to the k plus 1 over 2, shine x, plus 3 to the k plus 1 minus 1 over 2, cosh x. Boom, we proved it, because that is exactly what we want, but with k plus 1 in there instead of k. And so you go, therefore, true for n equals k plus 1. And then you trot out your standard sentence that you have to trot out every time for induction to show that it works completely by induction. Now for that, I mean, I could trot out a sentence, and I'm not having to do this exam, obviously. I did mine a long time ago. But I would always go to a mark scheme, go, right, what's their standard sentence that they're trotting out for my conclusive proof that this has worked by induction, and just repeat that sentence. You know, we as math teachers always have our own little kind of way of writing this out, and many of us maybe not include exactly what we need to say. So I'll just go to a mark scheme and just go, right, what's their standard sentence? I'll tell you what, I think I've got the mark scheme somewhere here. Bear with me a second. Let me see if I can find the mark scheme and tell you what their last sentence is. Talk amongst yourselves for a sec. Right, their standard sentence is, oops, coming up. Slick this, isn't it? If true for n equals k, let's see what they say. So they go for if true for n equals k, then also true for n equals k plus 1, which is what we've just basically done there. So the result is true for all positive integers. I usually put it by induction, I usually put this in. So by induction, result is true for all positive integers. There you go. That's it. Okay, it's a bit of an unusual one, but actually it falls out quite nicely once you start playing around with it and doing your differentiating.